Large language models do not write. When you submit a prompt, the AI doesn't think about paragraphs or narrative arcs. Instead, it runs thousands of mathematical calculations in parallel, assigning a probability score to every possible word in its vocabulary. Those thousands of choices collapse into a single, highly calculated token. Your written prompt is only half of that equation. It supplies the context. But operating silently beneath the surface are hidden algorithms dictating exactly how the model is allowed to interpret that context. These control algorithms are known as hyperparameters. By adjusting dials like temperature, top P, top K, max tokens, and penalties, you directly manipulate the underlying probability engine. To see the impact of these settings, we can run a single simple prompt, like describe the sunrise, or in Tamil, Surya Udayate Varni, Surya Udayate Varni, through two entirely different parameter configurations. Under the first configuration, the output is rigidly factual. The AI states, the sun rises in the east. Under the second configuration, using the exact same prompt, the output becomes highly stochastic and unpredictable. The AI writes, a hero of fire piercing the night's blanket. These variations aren't random. They are the result of adjusting specific numbers in the probability engine to force the model into either a precise or a creative mode. Every response from an LLM begins with a calculation. For every word in its vocabulary, the model generates a percentage-based score, reflecting the likelihood of it coming next. Imagine we feed the model an incomplete sentence, I came to eat, or non sapida. The AI calculates the next word is came at 70%, going sits at 20%, want at 10%. Dropping the temperature slider to 0 mathematically forces the AI to choose the highest probability word 100% of the time, resulting in reliable, repetitive text. If you ask a temperature 0 model to write a sentence about a cat, you get a dry, factual response. The cat is a domestic animal. Setting temperature to 1 preserves the baseline 70-20-10 proportions, allowing for natural conversational variance. Pushing the temperature to 2 flattens the distribution curve, artificially boosting the probability of rare words, making them just as likely as common ones. That same prompt about a cat now yields highly unpredictable and creative results. The cat sang to the moon. By scaling these percentages, temperature determines exactly how safely or how widely the AI samples from its distribution. High temperature creates a problem. It gives too much weight to the long tail, the thousands of nonsensical words at the bottom of the list. We need a way to filter that tail out. Top K acts as a hard numerical cutoff. It restricts the AI selection to a specific predefined number of top-ranked tokens. If you provide the prompt, the sky, or Vanam, the AI maps out 100 possible continuations. By setting top K to 5, the model immediately discards the other 95 possibilities. It can only pick from the top 5. Setting top K to 1 restricts the AI to a single choice, acting exactly like temperature 0. Top P, or nucleus sampling, provides a dynamic alternative, using a percentage-based threshold instead of a fixed count. If you set top P to 0.9, the engine sums up the probabilities of the top words sequentially. The moment those combined probabilities hit 90%, it strictly ignores the rest of the list. While top K is a rigid limit, top P is a flexible net. It expands or shrinks the pool of options based on how steep the probability curve is for that specific word. Standard engineering practice relies on this pairing. Keep temperature high to generate creative concepts, but lower top P to prune the most bizarre token choices. Together, top K and top P act as the structural guardrails of the probability engine, ensuring the model remains logically coherent even at high creativity levels. AI does not process words, it processes tokens. A token is a fundamental computational unit. A common English word like photosynthesis might split into 2 tokens. A complex Tamil word like Thiruvananthapuram fractures into many. The max tokens parameter directly controls the physical size of the AI's workspace. It limits the absolute length of the generated output. Practitioners constrain this number for 3 specific reasons: to control the computing costs billed by the API, to reduce the time it takes for an answer to generate, and to force concise formatting. The standard brackets are clear. You allocate 10 to 50 tokens for a yes or no answer. You allocate 200 to 500 tokens for a solid paragraph, and you allocate 2,000 or more for dense reports. However, max tokens is a ceiling, not a quota. If you set the limit to 8,000 but ask for today's date, the AI will provide the short answer and stop naturally. It is also critical to separate max tokens from the context window. Max tokens is the limit on what the AI writes out, while the context window is the absolute computational limit of your input prompt and the output combined. By setting hard boundaries on max tokens, you maintain control over both the visual length of the response and the computational cost of the query. One of the most common failure states in a large language model is the repetition loop. The AI gets stuck, outputting the same word or phrase over and over again. This happens because of context weight. Once a word has been generated, its statistical probability of being selected again increases. The AI defaults to what it has already established. The frequency penalty is a stacking mathematical weight built to break this exact loop. Every time a specific token appears, the frequency penalty subtracts from its probability score. If the model uses the word AI 5 times, it becomes mathematically difficult to use it a 6th. The model is forced to pivot to synonyms like machine learning or seierkai nunnaribu. The presence penalty targets a different problem. It is a flat algorithm that applies a one-time penalty to a token if it has appeared in the text at all, regardless of how many times it was used. This makes the presence penalty a novelty engine. The moment a concept is introduced, it gets penalized, forcing the AI to introduce entirely new angles and topics into the output. But if you max out both penalties, the model is mathematically barred from referencing its own context. The resulting text becomes vague and unreadable. When tuned correctly, these 2 penalties are your anti-monotony algorithms. They force the AI to continuously expand its vocabulary and conceptual breadth. The mathematics of hyperparameters only matter when applied to specific tasks. By mixing these 5 variables, we construct distinct operational profiles along the output spectrum. Profile 1 is for technical generation, like writing Python code or parsing data. Here, creativity is a liability. You need deterministic syntax. Temperature is locked at 0, top P at 0.1, and penalties at 0, because variables in code often repeat. Profiles 2 and 3 represent the middle ground, covering text summarization and customer support chatbots. For chatbots, temperature set between 0.5 and 0.8, with top P at 0.8. This balance prevents robotic stiffness while maintaining factual reliability. Profile 4 pushes into the realm of creative writing, tasks like brainstorming 10 brand taglines for a marketing campaign. Here, temperature hits 1.0 and top P opens to 0.95. High penalties are used to guarantee all 10 taglines are distinct, with no overlapping ideas. Profile 5 is pure artistic content, the territory of novelists and poets. We push temperature past 1.2, set top P to 1.0, and apply a high presence penalty. This combination forces the engine to generate wild plot twists and unique character descriptions. Calibrating the parameter profile to match the intent of the prompt ensures the final output meets the specific technical or creative requirements of the project.